Okay, fantastic, that's recording. Okay, so it's my great pleasure this week to welcome Alberto Cattaneo, who's going to be talking about AKSZ and general relativity. So please take it away.
Okay, so thanks for the invitation and the opportunity to present this work, which is actually joint work with my student, Giovanni Canepa, and my former student, Michele Schiavina. And well, it's mainly based on this recent paper and, well, several previous papers in collaborations with other people like Palatine and Nikolai Rashitiki. If it's okay for you, I arranged my PDF file to have a double-sided. So on the right, you will see the slide I'm presenting, but you still see the previous slide on the left. Okay. So actually, I think, well, I will not assume much. Well, probably your community knows well BV, maybe Bfv, but I will give a short introduction to that as well. And actually, I will start from very basic ideas. So my preliminaries are actually functional with the quantum mechanics, the functional integral presentation of quantum mechanics. So this is a bit heuristic, but it's there to motivate what I'm going to do next. And even though we are not quantizing gravity, but that's about the motivation. So the first point is just Dirac and Feynman presentation of quantum mechanics as a functional integral. So let's assume that you have an action, and for simplicity of notation, I already assume that the action depends on both the p and the q variables. So it's already the first order action, if you like, explicitly is like integral of p dq minus h dt. So it depends on some variable p dq and p and q, and so you should think of p and q either as coordinates on some cotangent bundle, or in this notation as a map from an interval to a cotangent bundle. Okay, so a path in a cotangent bundle. And the action is some local functional. So typically PDQ minus HDT integrated over the interval I. Now in quantum mechanics, what you're interested in is the evolution operator, that is the exponential of some quantization of the Hamiltonian function times t. And this h hat is a quantization of the Hamiltonian function h that appears inside the action functional. And what Dirac and Feynman observed is that, at least formally, you can compute the integral kernel of this operator. So this is a function of initial positions and final position as an integral of the exponential of the action. Oh, sorry, there should be a p as well here, since it should be in q, right? Weighted by I over h bar, and you integrate over all paths in T star n. Okay. And the initial position and the final position appear as initial and final condition for the Q path, the Q part of the path. Okay, so here, notice the mistake, the action depends also on Q. Yeah, right? We want to integrate on P. We want to integrate also over P. Okay. Now, so this is the standard answer, and there are several ways to make sense of this. I mean, Feynman, for example, showed that if you discretize this formal expression, you get something that converges actually to this operator. And another approach that probably the one we would use is to define this as a perturbative expansion. That is, you find a critical point, and then you formally expand around some Gaussian, and everything is expanded in terms of Feynman diagrams. And well, this formal expansion, which becomes a formal power series in h bar, gives the asymptotics of this integral kernel when this is somehow defined some other waves. Otherwise, in quantum field theory, is what you use to define this integration. I mean, one way to define this integration. Okay. So now let me describe some more details. So here I fixed the initial values and the final values of Q, right? So this corresponds actually, so for example, saying that Q at time 0 should be some point Q0 in terms of the cotangent bundle means that you're taking the cotangent fiber at Q0. So for example, this should be Q0 or Q1, okay? So choosing initial and final condition actually correspond to choosing some very particular Lagrangian submanifolds of this cotangent bundle. Basically, you fix one point on the base, you take the whole fiber, and this is Lagrangian. But more generally, you can choose other Lagrangian submanifolds, and this will correspond to writing the integral kernel with respect to different polarizations. So for example, if n is Rn, then you also can choose some horizontal polarization. So you can fix P, for example. You can fix the P variable, right? And then you have some other Lagrangian submanifold of T star Rn, which is allowed. And this would give you, for example, the integral kernel, say, going from the Q representation to the P representation. So these are the various possibilities. What I want to stress here, however, that the boundary symplectic structure is very important. So in this case, the boundary symplectic structure is just the canonical symplectic structure of the cotangent bundle of N. And this is very important because this is what allows you to choose a boundary condition, namely Lagrangian submanifolds, and in quantum mechanics, it's what allows you to speak of polarizations. These are, foliations or distributions whose fibers are Lagrangian. This is what you use, for example, in geometric quantization. Okay, so but the symplectic structure is fundamental. And actually, more generally, you can assume the target to be some symplectic manifold, not necessarily T star n, and you should try to make sense of this. Of course, this is much harder. And what was typically, if you really work, define these as perturbation theory, what you do anyway is to take some classical solution and then perturb around it, and then, well, locally, you go back to this situation anyway. Then, okay, another issue is how to globalize this result. Moreover, you may allow this S to be infinite dimensional. So this becomes a quantum field theory. It's not the usual way you present quantum field theory, but here I want to stress that I want to think of quantum field theory as somehow quantum mechanics on some infinite dimensional symplectic target. So let me explain this in the example of the scalar field. So suppose that you have the n-dimensional scalar field, but you assume that your n-dimensional manifold has a form of a cylinder. So it's in some interval cross some manifold of dimension n-1. Okay, and actually in this talk, I will only consider cylinders. So my bulk manifold will always be of this form. Okay, so the scalar field is just a function on the manifold I cross sigma, but you can think of a function on I cross sigma as a path from the interval to the infinity function on sigma. Okay, and so this is somehow the idea. So instead of thinking of your field theory as a field theory on I cross sigma, you think of it as a theory of paths in infinity sigma. Okay, so this is your infinite dimensional target. So this is not symplectic yet. So because actually I just introduced the position variables, my phi now are the position variables. I will also introduce their momenta. And well, in this case, the momenta are also a function on sigma. So my target symplectic manifold, which generalizes T star n, is just the direct sum of two copy of functions on sigma. And the symplectic structure is just induced by the pairing. So it seems, well, here in the scalar field that there is some background metric. So this will give you some volume form on sigma. So if you have two functions on sigma, you can pair them this way. Just we multiply and integrate it. This is a non-degenerate pairing. And then by taking essentially the skew symmetrization of this pairing over here, you get a symplectic structure. So this is the analog of the canonical symplectic structure on the cotangent bundle of Rn. But now Rn is replaced by this infinite dimensional space. Okay, so now you have rephrased the scalar field as mechanics, classical mechanics, with target this infinite dimensional symplectic manifold. Okay, so this is a bit formal, and anyway, I will not do quantization, but this is to motivate some classical or BV considerations where I will have to use such spaces. Okay. Now, the next step is to extend this not only to infinite dimensional target, but actually to extend the whole construction to degenerate actions. Right? Because when you, for example, you have gauge theories, and particularly in general relativity, your action functional is degenerate. So the non-degenerate action is, well, a nice case you have in classical mechanics, for example, PDQ minus HDT. Non-degenerate means, I mean, from the point of view, I mean, there's several almost equivalent meanings. What I mean here is that, for example, when you take a classical solution and expand your action around the classical solution, there is no linear term because the classical solution is a critical point of the action, and you assume that the quadratic term is non-degenerate. So this is what I mean by a non-degenerate action. And this is what happens in mechanics, like PDQ minus HT has this property. And so this is why you can formally define the functional integral as a formal expansion around a Gaussian measure. Okay? But if this quadratic form is degenerate, this is no longer allowed. And this is typically what happens if you have symmetries. right? In gauge theories, in general relativity, or symmetries, having symmetries means that there are some vector fields that leave your action invariant. And this means that, in particular, this quadratic form must be degenerate because it will be constant along the, we will have a kernel along the distributions that describe the symmetry. Okay, so you have to do something. I mean, in physics, you know what you do. You have to do some gauge fixing. But the important thing is not only just to gauge fix. This will be arbitrary. You want to be able to keep track of gauge fixing. It is you need some procedure that tells you not only how to fix the gauge, but also that tells you that nothing physical changes when you change the gauge fixing. Okay, I will explain what I mean by this, and explicitly I will explain it in the Bfv formalism. So the formalism I'm going to describe here is the Bfv formalism coupled with the Bfv formalism on the boundary. I think most people in Prague are probably expert on Bfv, but I will recall it. From the physical point of view, Bfv is some development of BRST, which is itself a development from the Faddeev-Popov idea of introducing a particular determinant expressed in terms of an integral of a ghost variables. I will use Bfv because Bfv is much more flexible than BRST, and because it has a nice way to be coupled to the boundary. And so the two characters of my story would be the Bfv formalism, named after Batalin-Vilkovisky, and the Bfv formalism, named after Batalin-Fradkin and Vilkovisky. So their structure, the mathematical structure, is very, very simple, very similar. Well, basically, one is just the other with different gradings and different parity convention. But they actually address two different problems, both coming from field theory. Bfv formalism addresses the problem of fixing the gauge and keeping track of what happens when you change the gauge fixing, whereas the Bfv formalism addresses the problem of giving some cohomological resolution of the reduced phase space for field theory. And what is important for us, since when we go back here, we want to generalize this formula for the integral kernel, we need to have some way to let the bulk talk to the boundary. And the idea is that if we let the bulk be described by the Bfv formalism and the boundary be described by the Bfv formalism, and then there is a nice way to let them talk to each other. And this is what I developed with Pavel Mioff and Nikolai Reshetiki. So let me just recall the Bfv formalism now. So this is probably well known to everybody, but just let me go at least to introduce my notation. So the data of the Bfv formalism is, first of all, some graded supermanifold. And well, for us, this graded supermanifold will be infinite dimensional, will be this called Bv space of fields. It will contain, in particular, the physical field of the theory plus some additional fields. For example, the ghost and the momenta for both the ghost and the fields. But for the moment, just think of it just as some abstract graded supermanifold. On this graded supermanifold, you assume that we have an odd symplectic structure of degree -1. So by graded supermanifold, I mean a supermanifold, so there is some parity, which in particular tells you which coordinate, which local coordinates are even and odd. So locally it tells you that your algebra of function is some infinity algebra tensor to some exterior algebra, right? But in addition, there is some grading over Z, which is called the ghost number in physics, which is, well, useful for bookkeeping. And so I will use them. And typically they are not related. I mean, these are a class of theory, for example, AKSZ theory, where I come back to the end, where the parity is actually the Z grading modulo 2, but in general, they are different. Particularly, well, this Z grading says that Z grading equal to 0 is the degree that you assign to the physical fields. The ghost have degree +1, and so on. Okay, so here the data are then a not symplectic structure of degree -1 and an even function of degree 0, which satisfies the so-called classical master equation, where this round bracket is just the Poisson bracket induced by this symplectic structure. Okay, so okay, here I'll make a pose. So if the manifold is finite dimensional, of course, the symplectic structure gives you some Poisson bracket. If the manifold is infinite dimensional, like in the case I want to consider, you don't have, I mean, you cannot invert the symplectic structure, so you cannot define a Poisson bracket by inverting the symplectic structure, but still you can define the Poisson bracket on some functions. So in this case, the second statement means that S is in particular a function for which you can define the Poisson bracket. Okay, and this function of the even function of degree 0 is an extension of the classical action. So in particular, it's a classical action, which is of course of degree 0 because it depends on the physical field that have degree 0, plus some additional terms. Okay, and these additional terms are added in such a way that the new action becomes non-degenerate when you do the gauge fixing, and moreover that it satisfies this equation. Okay, so Batalin-Vilkovisky actually gave a procedure to construct this S out of the classical action. So basically you start on your classical action on some space of fields F. In addition, you have symmetries, and then you add pieces to your classical action that encode the symmetries, the Lie algebra of symmetries, or some Lie algebroid structure of the symmetries, or actually even weaker, the on-shell Lie algebroid structure of symmetries, whatever, but you can always add this additional term. And actually, this can be done and is unique up to equivalences if you start with enough symmetries. Okay, so this, I will not go into this, but I mean, this is the classical result, which has been actually re-examined recently by Felder and Cattaneo in the finite dimensional case in algebraic geometry. But essentially, the important point here is that if you put enough condition, this solution of the classical master equation is unique up to appropriate equivalences. Okay, for quantization, you actually need something more. You need the quantum master equation, which is this equation here, where you introduced now the variable h bar, which is Planck constant, and you introduce this extra operator, which is called the Bfv operator. I will not talk about this in the talk, so just let me make this digression. There is this additional operator you can define on a odd-symplectic manifold, and at least if it's finite dimensional, so you can make sense of this equation, and you see that for h bar equal to 0, this is just a classical master equation. Okay, so you should think of this equation as a deformation of the classical master equation. You may try to start from a solution of the classical master equation and to deform it to a solution of the quantum master equation by adding possibly correction. Sometimes this is possible, sometimes there are cohomological obstruction to do it, but let me assume that this is possible. And of course, if you are doing field theory, there is an additional problem that this delta is not defined when you start with, so you have to introduce a regularization to make sense of this delta, to make sense of this equation, and so on. But formally, assume that this is done, or that you are in the finite dimensional case, then Batalin-Vilkovisky's theorem says the following. If S satisfies this equation, and you integrate the exponential of S times I over h bar over a Lagrangian submanifold of this graded supermanifold F, the result is invariant under deformations of L. Okay, so this is a crucial result, which is somehow some sort of a supermanifold generalization of Stokes' theorem. Okay, this is actually in the infinite dimensional case, this is actually a theorem. In the infinite dimensional case, you have to make sense of it by some regularization. And now the application of this is to think of this as gauge fixing. So the choice of this Lagrangian submanifold is what corresponds to other physical prescription to make a gauge fixing. And this theorem tells you that this result is invariant under the formations of L is what you want to have. So basically, you want to be sure that when you change your gauge fixing, the result doesn't change. Okay, and now let's go back to our original problem. So what we want to do is actually to compute the integral kernel. So now assume that your space of Bfv fields is actually some space of function or more generally differential forms on our manifold, which has the form I cross sigma, well, taking values in some target. So here take some tensor, some V, but actually this could be some infinite dimensional target, and so then it should be some completed space, doesn't matter. And moreover, I want to think of this as actually pass into differential forms of sigma tensor V, or actually differential forms on the interval, taking values in differential form of sigma tensor V. Okay, so anyway, we have this expression. Now the idea is that you integrate the exponential of the action over some Lagrangian submanifold of the space of fields, and you fix some endpoint values of the field, some phi 0 and phi 1, that correspond to some, well, Lagrangian some manifold, some symplectic space of boundary fields that I haven't introduced yet. Okay, but suppose you can do that. Now, the problem is that this Bfv theorem is not enough for your purposes because, well, when you're doing this, it turns out that because of boundary terms, I mean, typically when there is some integration by parts involved here, so when you try to apply the bulk theorem to a situation like this, we are in trouble because there are some boundary terms. And so this tells you that this expression, which is well defined, because when you do the gauge fixing, the action becomes non-degenerate, so you can do the expansion in Feynman diagrams. However, what happens here is that when you deform the Lagrangian submanifold, the result changes. Okay, so in this case it didn't change, but now it changes because of boundary terms. Okay, so what you have to do, you have to improve the Bfv description and find some equivalences on the space of this integral kernel in such a way that when you deform this Lagrangian submanifold, K just changes by an equivalence. Okay, so this is my next topic. Before, however, I have to describe the boundary structure of the field theory, and in particular describe it in the Bfv formalism. Now, let's just start from the classical picture. So suppose that you have some local field theory on I cross sigma, and assume that it satisfies some regularity assumption that I will not discuss here. So these are some good assumption that allows you to do what I'm describing here. And well, the regularity assumptions are satisfied in several field theories, including general relativity that I will describe at the end. So, okay, suppose that, okay, you start with your field theory, classical field theory in I cross sigma. Then what you observe is that actually this field theory will give you some space of boundary fields that I denote by F sub sigma with some symplectic structure. So in our original example, PDQ minus HDT, right, pass taking values in T star n, the space of boundary fields is T star n with its canonical symplectic structure, right? But, and actually you see P star n from the PDQ term, right? Basically the PDQ terms becomes actually the canonical one formed on the cotangent bundle, and so you also get the symplectic structure. In general, what you do is, well, you compute the variation of the action. This is what's supposed to give you the Euler-Lagrange equation. Check what the boundary terms are, and try to interpret the boundary terms as a one form on some space of boundary fields. Okay, and then its differential will be the symplectic two form. Now, since this is a result of an integration by part, you see that the boundary fields will be essentially the restriction of the fields on the boundary plus some of their transversal jets. So, for example, in the classical mechanics, well, in the PDQ setting, you just see the restriction of P and Q on the boundary. But if, for example, you started from the action in the form like the usual kinetic term, 1/2 of Q dot square, so it depends on your Q. When you go to the boundary, you will see that you need both the value of Q on the boundary, but also the value of Q dot on the boundary to describe the boundary one form. So in this case, you have to retain one jet, which is the velocity. And so for this reason, the symplectic manifold associated to classical mechanics is the tangent bundle. And usually you prefer to move to the cotangent bundle, passing from velocity to momenta, but that's essential from this part of view. Okay, so but in general, you can do this construction. I mean, there are abstractions, so that's why I speak of these regularity assumptions, but this is okay, for example, in Yang's theory or in general relativity. And at the end, I will describe the example of general relativity, so you will see explicitly how this is done. Okay, so this symplectic manifold of boundary fields is a space of potential initial conditions, but it's a bit too large. Right? Because if the theory is degenerate, there are some constraints that have to be satisfied, and these constraints have to be satisfied even on the initial conditions. Okay? So this would be some sort of reference, symplectic space of boundary fields that doesn't know about the constraints of the theory. And what you have to do is to impose the constraints. Right? The initial conditions must satisfy the constraints. So your action will give you, in addition to this symplectic manifold associated to the boundary, also some submanifold, C sigma. Actually, I assume that this is a submanifold. It will give you some constraints, but so some subset, but I assume that it is a submanifold. And in the good cases I want to consider, I assume that this submanifold is actually co-isotropic. So co-isotropic means, let me give you the simplest description, means that locally the constraints that define the submanifold are first class, which means that their Poisson bracket, with respect to the symplectic structure on this space, are linear combination of the constraints again. Or in other words, the Poisson brackets of the constraints vanishes on C sigma. Okay? Or in other words, the Hamiltonian vector fields of the constraints on C sigma are tangent to C sigma. And actually, the span of these Hamiltonian vector fields is precisely the kernel of the restriction of the symplectic form to C sigma. Okay? So actually, this tells you that actually you can define a quotient here. You can mod out C sigma by this kernel or by the Hamiltonian vector field of the constraints. And this gives you what is called the reduced phase space. Okay, and again, my next assumption is, well, for a moment, I will drop this assumption later on, but for the moment, let's assume that this quotient is also a smooth manifold. And then it's automatically endowed with a symplectic form. You just take, you restrict the symplectic form from F sigma to C sigma. Here it is degenerate, but on the quotient is non-degenerate again. Okay, so this is a new symplectic manifold, and this is the true phase space of the theory, right? Because, well, you impose the constraints on the initial conditions, right? And moreover, you have their momentum. This is what this construction corresponds to. Okay, and so basically the boundary condition we are talking about at the beginning will have to be Lagrangian submanifolds of this reduced phase space. Now, just to give you an idea, let me do the example of electromagnetism. Now, in the case of electromagnetism, so I will not go through this construction, it will take too much time. Let me give you the result, because probably you're familiar with the result. So the boundary fields of electromagnetism are actually the electric field and the vector potential. So I think of them as a vector field on the boundary manifold sigma, and as a one form on sigma. Okay, so these are the two fields. And this space, one form plus vector fields, is actually a symplectic manifold if you have a volume form on sigma. For example, the volume form coming from some metric structure. You have some background pseudo-Riemannian metrics in electromagnetism. So on this space, you have a pairing. So if you have a one form A and the vector field E, you can pair them together, you get a function, and then you can integrate this function using the given volume form. Okay, so this is non-degenerate, and again, you can use this to induce a skew-symmetric two form over F sigma. So this would be the symplectic structure. Okay, so in other words, you might think of this pairing as formally as some way of identifying one forms as dual of vector fields. Okay, so this is again some sort of cotangent boundary. Now, the point is that if you look at Maxwell's equation, there is one equation that does not involve time. Right? Divergence of E equal to 0. I mean, you have to rewrite Maxwell equations in terms of the electric field and the vector potential. So the magnetic field is no longer a free variable. It will be deduced from the vector potential. And but then you have a Gauss law that says the divergence of E is equal to 0. Right? This is not an evolution equation. This doesn't change with time. This is a constraint. So whenever you fix the initial condition, you have to impose this condition. Right? You cannot start with any electric field. You must start with an electric field that satisfies Gauss law, and then you let your system evolve. Okay, so your C sigma in this example is a space of solution to Gauss law, and then you have to compute the Hamiltonian vector fields to this Gauss law, and it turns out that well, they act on the vector potentials essentially by gauge transformations. So in this case, this reduced phase space, namely the quotient of this sigma, this means the symplectic reduction of C sigma, is exactly the same as the space of solution to the Gauss law modulo gauge transformations for the vector potential. Yes?
So in classical electromagnetism, you have the symmetry between the electric and the magnetic field. Mm-hmm. Can I do the same thing here with the B field instead of E? Like I could.
Yes, because yeah, you can. Yeah.
Like I mean, it's just basically just changing your
well,
point
if you
right?
start for free electromagnetism, of course.
Yeah.
Because if you have electric charges, then the
sure. In a vacuum, yeah.
Divergence will be equal to 0. You have some, so yeah, sure.
Okay, awesome. Cheers.
I mean, even if you have charges, you can try to generalize it, but okay. Okay. Now, the problem of this construction is that the symplectic reduction is usually singular. I mean, as I told you, in most example of a field theory, the space sigma is actually a submanifold, a coisotropic submanifold. But this is not a problem. But the problem is that its reduction is usually singular, very, very, very singular. Moreover, even if it were not singular, it would be some very complicated symplectic manifold. Whereas the space of fields we started with is typically, for example, in the case of electromagnetism, but actually also in the case of general relativity, at least if you present it in the coframe formalism, this space F sigma usually is some affine space. Okay, so on this space F sigma, everything is simple. It's an affine space with a constant symplectic structure, whereas on the symplectic reduction, you get something very, very complicated. And even worse, very often the symplectic reduction is singular. Okay, so this is not a good idea to go to the quotient. And the good idea is to do a cohomological resolution. And this is what Batalin-Vilkovisky-Fradkin and Vilkovisky did. So now let me explain this here. So first of all, let me introduce the data of a Bfv space. These are the same as what we saw for a Bv space. So here, what was it? Yeah, here. But with some changes in the condition about parity and grading. So actually, I displayed in pink the differences. So the data for a Bfv manifold are the following. You start with the graded supermanifold. I will call it F sub sigma because our main example would be something associated with the boundary sigma. Now, instead of having an odd symplectic structure of degree -1, we have an even symplectic structure of degree 0, which I will denote by omega sigma. And instead of having an even function of degree 0, we now have an odd function of degree +1. Okay, but still we want this function to satisfy the classical master equation, which is here. And now this pink curly bracket is just the Poisson bracket associated to this symplectic structure. Okay, so the only difference formally is just the grading. Now omega is even instead of being odd, as degree 0 instead of having degree -1. S is odd instead of being even, and as degree 1 instead of having degree 0. Okay. Now the physical part of this, so in the previous case, the physical part of the description was contained in S, which was a function of degree 0, and in particular contained a term that depended on the physical fields. And here, the physical part is contained in, well, in omega. Omega is even and of degree 0, and so in particular, well, there will be some subspace. There will be some actually ordinary submanifold inside F sigma, symplectic submanifold in sub F sigma, which consists just of the physical fields, right? And well, this symplectic structure is contained here. Okay, now what is the relation between this Bfv theory and the problem of symplectic reduction? Well, the idea is the following. This was actually done by Batalin-Vilkovisky-Fradkin and Vilkovisky, and then put more on mathematical background by Eugene Tashev, at least for local constraints, and by my former student Schatz, who did it globally. So the idea is the following. You start with some symplectic manifold, F sigma, and suppose that you have some quasi-tropic submanifold, C sigma. So it means locally this is described by first-class constraints. Now the idea is the following. You extend your space, your classical symplectic manifold F sigma to some graded supermanifold F sigma with an even symplectic structure of degree 0, which contains F sigma as a symplectic submanifold. And you construct some function S sigma, or this S Bfv here. So this is an odd function of degree 1. Then what you do, you take the Hamiltonian vector field of this function. By the classical master equation, this Hamiltonian vector field squares to 0. It's what is called a cohomological vector field. And by the choice, it's odd by the choice of parity, and it has degree 1 by the choice of degree. So it's really what is called a cohomological vector field. So what you can do now is to compute its cohomology. And the result is that if the symplectic reduction is smooth, this cohomology in degree 0 is precisely the Poisson algebra of functions on the symplectic reduction. Okay, So in the good case, this is just a new way to rephrase what you want to have. But now the advantage is that this is now well, justified in terms of homology, and this is something you can do in general. And actually, again, the idea is that instead of consider your coisotropic submanual sigma, you consider this Bfv data. The idea is that you could recover the functions on the symplectic reduction by computing the homology in degree 0, but this is not what you want to do, right? Because, well, typically this quotient is singular, and actually typically this space of functions on the quotient, this is actually the invariant functions, is very, very poor, contains very, very few information. So for example, if the quotient is not Hausdorff, you only have constant functions here. So you don't want to go to the quotient. Actually, the idea that you want to stay at this stage. So the idea that what is important is a complex. Now, not the complex, and actually, well, this addition structure that gives some Poisson structure on this complex, right? But you don't want to go to homology. Actually, now your new category is the category of complexes and with the chain maps as morphisms. Okay. Now the idea is that this setting, in addition to giving you a nice way to describe this singular quotient, also gives you a good recipe for quantization. So the idea is the following: suppose that you are able to quantize this graded supermanifold F sigma. Right? And actually, in typical example, this is actually some affine space or some vector space, so this is not a big deal. Moreover, you want to quantize the function x sigma to some operator, right? That's what you do in quantization. And now the crucial point that you want this operator, so this will be an operator acting on this graded space, you want this operator to square to 0, okay? And this is a non-trivial condition. I mean, the classical master equation that was here is just the lowest order term, right? This classical master equation tells you that whatever quantization omega you take, omega square is equal to 0 up to order h bar, okay? But might have a higher correction, okay? So you have to look for a quantization that have this property. This is a non-trivial condition. You might try to work, say, by deformations of the classical theory, but there are cohomological obstructions. So actually, this is a very non-trivial condition, and actually this is one place where you might see the so-called anomalies of a field theory. The obstruction to solving these equations are related to anomalies. Okay, but suppose that we can do that, then we can define a new vector space, right? Just by taking the cohomology of this graded space in degree 0. Okay, so now instead of taking q sigma as a boundary operator, we take this quantization omega sigma. So this is a quantum version, right? And the idea is that we define this to be the Hilbert space of the reduced phase space. Again, the reason is that in good cases, so in good cases, we know that this classical cohomology is the algebra, the Poisson algebra function on the reduced spaces. And in good cases, this quantum cohomology is really a geometric quantization of this reduced phase space. Okay, but now we want to extend it to the general setting. Okay, so this becomes now the definition. Okay, now let's go back to our problem, right? We had some Bfv theory, but now we allow for a boundary, and we want to fix some boundary conditions for some of the fields. So this will be related to some Lagrangian submanifolds, and we want to compute this integral curve. Now we know a bit more than before. So for example, this boundary condition or initial final condition phi 0 and phi 1 should be related to some Lagrangian submanifolds, but now of this space here. Okay, now we have this symplectic space associated to the boundary. Okay, so now there are two Lagrangian submanifolds that come into play. There is a Lagrangian submanifold of the space of bulk fields. This is used for the gate fixing, and is it too small or is it okay?
It's a little.
Oh, okay.
That's better. Yeah.
Okay. So, and there is another other two Lagrangian submanifold actually, right? That we have to choose. These are Lagrangian submanifold of these graded even symplectic manifolds associated to the boundary. You have to choose a Lagrangian submanifold for the initial point of the interval and the Lagrangian submanifold for the final point of the interval. And these are the boundary conditions, right? These were phi 0 and phi 1 live, right? And so you can now make this computation. So you can compute this integral kernel, right? And the point is that this will be the integral kernel for some operator of the whole graded space. Okay, but what we are looking for is the integral kernel for some operator in this cohomology. So the important point here is that you want that this integral kernel K is killed by omega sigma. Okay, so this is important. So, and moreover, you want to be sure that when you deform the Lagrangian sum manifold that defines the gauge fixing, the BV form is now ensures that this K changes by an exactor. Okay? So if you're able to set things in such a way, then the cohomology class of K, I mean, because the condition, you can consider the cohomology class of K inside here in the physical Hilbert space. And the second condition tells you that the physical value of K in this cohomology class is invariant under deformations of the gauge fixing. Okay, so this is exactly what you want to have. Okay. Now, is this possible? Well, as I told you, there is already this problem to find omega sigma the square to 0. And in addition, now you want an omega sigma that has these additional properties, right? So this should probably also know something about the bulk. Now, this is where comes my work with Pavel and Nikolai Reshetikhin. This is a pairing between the bulk BV and the boundary Bfv formalism. And this is a pairing that under some condition ensures you that you can do that. Okay, so you can actually construct an omega sigma with these two properties. Now let me now first start with the mathematical data of this Bfv formalism. So we have some BV data and some Bfv data. So the Bfv data are as before. So it's an even symplectic manifold. So it's some graded supermanifold with an even symplectic form of degree 0, a function, an odd function of degree 1 that satisfies the classical master equation. I explicitly write here its cohomological vector, it's a Hamiltonian vector field. I mean, this is not an extra piece of data, can be induced from the rest, right? The X assumption I make for simplicity, I mean, it can be relaxed a bit, is that I want the symplectic form to be exact. Okay, so and explicitly I actually want to choose a one form alpha sigma here. Okay, this is not the stricter version of this formalism, but I mean, I will use this for simplicity. Otherwise, well, several formula becomes more complicated. Now, to the bulk, we associate some sort of BV data. Right, so by BV data, I mean now some sort of BV data. It means the following: we have a graded supermanifold F, we have a not symplectic form omega of degree -1 as before, we have a function S, which is even and has degree 0, and we have a vector field Q, which is odd and of degree 1. Now, in the true BV data, we would have required that S satisfy the classical master equation. We would have defined Q as its Hamiltonian vector field, and then the condition that Q squared to 0 would be automatic. Okay? Now we relax this condition. So what we retain is a condition that Q squares to 0. Okay? But we no longer insist that S satisfies the classical master equation. We don't even insist that S allows a Hamiltonian vector field, and we don't not insist that, of course, Q is a Hamiltonian vector field. Right? So the condition, the correct condition are spelled here. So one are just the conditions for a Bfv manifold, as I said before, plus a condition that this Q sigma is precisely the Hamiltonian vector field of sigma. The second condition is that Q is an odd vector field of degree 1 on F that squares to 0. Okay. The third condition, which is new, is that there is a compatibility. So what I wrote here, this is pi. So this pi is a surjective submersion from F to F sigma, and I want Q and Q sigma to be pi related. So one way to express this is for every function on F sigma, you can either take its pullback and then apply Q, or you can first apply QS and then pull back, and they should be the same. Okay, so this is a compatibility between Q and Q sigma. Okay, and finally, there is this new equation that we call the modified classical master equation, which replaces the old condition that Q should have been the Hamiltonian vector field of S. Right? So this would have been the BV condition, because this condition plus this condition here would be almost equivalent to the condition that S satisfies the classical master equation. Now we relax this condition, we say that, well, this is true up to the pullback of this one form. Okay? So these are the data. And well, why do we come up with this data? Well, for two reasons. First, because we can construct this data in field theory, and second, because they will allow us to get a quantization with these properties. Okay, so our results, and then let me move directly to the quantization. Our result is that for, well, several examples of field theories, where now F and F sigma are the spaces of fields. So actually F sigma is the Bfv space of boundary fields, and F is the Bv spaces of fields for the theory without boundary, which is just blindly extend to the case with boundary. Okay, so you just take the same space of fields and the same action functional, right? But now, because of boundary term, the equation IQ omega equal to ds will no longer be satisfied, and this term here precisely keeps track of the boundary term. Okay, so assume that we start from this data and assume that the theory is good enough, then we can produce omega sigma perturbatively in such a way that these two properties are satisfied. So for this integral kernel, so both omega sigma and the integral kernel are defined perturbatively, and they satisfy these two conditions. So particular, omega sigma applied to k is equal to 0, and when you deform the gauge fixing, k changes by an omega sigma exact term. And this omega sigma is a quantization of S sigma. Okay, so almost everything is okay. Something that is not guaranteed by this construction is that omega sigma squares to 0. So this is something that you have to check, and sometimes there is no way it could work. These are again related to anomalies. So from now on, let's assume that you are in the good situation where we can do this construction in such a way that omega sigma squares to 0. And there are plenty of examples for that. Right? So how is this done? Actually, what we do here is, well, one way to produce this data is the following. So this is actually the way we discussed with the Pavel and Nikolai Reshetiki. You actually start from the BV data in the bulk. You look for the boundary term when you integrate by part in here. So these are here. And you realize that this data gives you some sort of pre-Bfv data. So basically, they will give you something like here with all these properties, apart from the non-degeneracy of omega sigma. Okay, and then the idea that, well, if you have this data with omega sigma degenerate, well, you can do some symplectic reduction, and then you get the good Bfv data, right? And this is actually the procedure that we may apply to several field theory. For example, this works for Young-Mills theory. It works for general relativity in the Einstein-Hilbert formalism. But for example, it doesn't work for general relativity in the coframe formalism, right? And where it fails, and when you do the reduction of this pre-Bfv data, because this reduction turns out to be singular. Okay. So there is another way. So these are, for example, example of theory where it works. There is another, but it does not work for the coframe formalism, which is also known as Palatini-Cartan formalism for general relativity. So there is another way to do it. So first of all, let me tell you why we're interested in the Palatini-Cartan formulation of general relativity. Well, the reason is that unlike the Einstein-Hilbert formulation that is based on a metric tensor, this is based on differential forms. And this is much nicer because, well, differential forms behave much better when you have boundaries and corners. You just restrict them. Okay? So this, eventually, we are even interested in studying corners of the theory. We prefer to work in this Palatini-Cartan or coframe formalism. But the problem is that this recipe we had with Pavel and Nikolai doesn't work here because these pre-Bfv data have a singular reduction. So here where it comes an alternative construction, and this is what I will describe in the last part. And the idea is the following. There's a pairing between Bfv and AKSZ. So I already said what is Bfv. So first of all, you take the classical theory, you consider the quasiotropic submanifold of constraint initial conditions. You describe this by BFD, as I explained before. So this will give you the space of BFD data. These are non-singular BFD data. Okay, so this is a good starting point, right? But they are not related to the BV data now, right? I'm just considering the classical theory. So what we propose to do now is to construct a BV theory, a bulk BV theory that is compatible with this boundary BFV data. And this is the AKSZ construction on cylinders. So let me explain what the AKSZ construction is. It stands for Alexandrov, Kontsevich, Schwarz, and Zaboronsky. And this is the following. So start with some and I explain it only on cylinders because it makes it a bit easier, and this is the case I'm interested in. So suppose that you have exact Bfv data. So we have this again, a super graded manifold F sigma together with an exact even symplectic form of degree 0 and some function S sigma, which is odd as degree +1 and satisfy the classical master equation. Okay. Then what you do, you consider the supermanifold of maps from the shifted tangent bundle of I to this target, which is also supermanifold. We'll not explain what this means, but we'll tell you explicitly what it means, and in the next slide I will make it even more explicit. This space essentially consists of 0 forms and 1 forms on the interval, taking values in coordinates of a sigma with no constraints on the degree. Okay, so this is not a space of morphism. This is why it's called a space of maps. The space of morphism would impose also a compatibility condition between the degrees of the 0 and 1 forms and the coordinates. Right? We drop that. So let's do this explicitly. So suppose that you have PQ coordinates on this target symplectic manifold, and this alpha sigma is the usual PDQ form. Now P and Q are possibly even and odd variables. Okay, but they have the same parity. And of course, this is not the most general form you could have, but I mean, I will focus on this one. Now, in this AKSZ formula, what you do is a formula. You replace the coordinate qi by a sum of 2 fields, q twiddle I and q hat I. Q twiddle I is a map, right, from the interval to qi. I mean, to the target, so it's a function. So q twiddle I is a function on the interval, and q hat I is a 1 form. And similarly for the p variables. Okay. Now, as I said, these are not morphisms, so the degree are not preserved, and the mismatch of the degrees is what is called the degree of the superfield. So if the coordinate qi is degree k, we assign degree k also to this function, but we assign degree k minus 1 to the 1 form. Okay. Now, the momentum will have degree minus k because the symplectic form is degree 0, and then this function will also have degree minus k, whereas this 1 form will have degree minus k minus 1. And then what you do is the following. You write down the BV action as follows. You integrate over the interval this 1 form. So in the first term, you take p twiddle dq twiddle, right? P twiddle and q twiddle are functions, so this is the form, and it has degree 0, right? So this is okay. And on the second part, what you do is the following. You take the function x sigma, and instead of evaluating it at qp, you evaluate it on this non-homogeneous sum of forms, right? Then you tell to expand this function, you select the 1 form, and you integrate. Now the result by AKSZ is that this function, I mean, you can also use this target symplectic form to construct a non-symplectic form over here. Simply, essentially, the q twiddle are the moment of the p hat, and the p hat are the moment of the p twiddle. So this gives you the odd symplectic form of degree minus 1. And this function S satisfies the classical master equation with respect to this symplectic form. So these are the results of AKSZ. And moreover, you can easily, I mean, this is not really a new result, it's just working out what is written in AKSZ. If there is a boundary, you can easily see that this bulk BV structure is compatible with the boundary BFE structure precisely as is in these axioms. This is almost obvious. Okay, so this is now, in a sense, we are done because now we have produced a bulk BV theory with compatible boundary BFE theory. Right? And this is a good starting point for quantization. Now, what does this new BV theory has to do with the original theory? Well, in principle, almost nothing, but okay, you will say more in a moment. So basically what you can do is, well, first of all, take this BV action and just evaluate it on the fields of degree 0, the physical fields, right? This will give you some classical action, and in addition, there will be some symmetries. So this will give you some physical theory, and you have to interpret it. Now, if your original theory, so first of all, as you notice here, this theory is clearly invariant under the parameterization on the interval. So if your original theory was not invariant under the parameterization, then of course this new theory has very little to do with the original theory. But if the original theory were, if the original theory was invariant, then you might expect that this new theory has something to do. Actually, well, it has something to do, but typically you cannot expect this new classical action to be your original classical action. Actually, in general, you can't even expect that the new classical fields are the same as the original classical fields. Okay, so I will actually discuss two examples to tell you what happens, and these are two relevant examples. So the first example is the Einstein-Hilbert formulation of general relativity. So this is a usual Einstein-Hilbert action. So lambda is a cosmological constant, so it's a constant, and the field is G. So G is a pseudo-Riemannian metric on M. Okay, so this is a classical action. So what you can do here, you can compute its BV action, applies the first recipe to produce the compatible Bfv boundary structure. This works very well. This is an old work I did with Michele Schiavina. So this works. In principle, you don't need to do this AKSZ construction, but you can also do it. So the other thing you can do, you can construct the space of boundary fields, compute the first class constraints. These are what are called the momentum Hamiltonian constraints in the general relativity literature. You can apply this AKSZ construction, so this should be a Z, and then you can check what happens. And well, the resulting theory is actually in some sense equivalent to this one. It turns out to be not exactly the same. It simply turns out to be the BV version of the first order formalism for this theory. So the first order formalism here is that here we have just the action depending on the position variables. What you have to do is to compute its momenta and then do the property of the Lagrangian transform to get the first order formalism. And well, the AKSZ construction produces the BV version of the first order formalism. So this is nice. And now let's move in the last few minutes to the Palatini-Cartan formalism. Maybe let's just stress here. These theorems are okay if space-time has dimension larger than 2. And you have to assume that the pseudo-Riemannian metric is non-degenerate on the boundary. So for example, on a Cauchy surface, this is okay. Okay, now here this is a coframe formalism. So this is the action, and here are the fields. So M here is a manifold. Again, assume that is dimension larger than 2. The field E is so-called coframe, or the field line. So these are just isomorphism between the tangent bundle of M and some reference vector bundle, which of course has to be isomorphic to the tangent bundle. Okay. And omega is just the one-form connection for the associated orthogonal bundle to this B. Okay. Now, my notation, omega KL, will be the notation for section of the exterior algebra of the cotangent bundle, tensor the exterior algebra of this reference vector bundle V. Okay. And in particular, you can see that E is a 1-1 form, right? It's a bundle map from TM to V, so in particular, it's a 1-1 form with respect to this notation. And moreover, you have the condition that it is non-degenerate. On the other hand, using the fiber metric, so here you need some fiber Minkowski metric, you can identify connections, right, as an affine space model on 1-2 forms. And moreover, you can check that the curvature is a 2-2 form. Right? The curvature is a 2 form, taking values in the Lie algebra, but the Lie algebra turns out to be just skew symmetric matrices, which is a wedge 2 of V. Okay, and so now you can make sense of this. So E is a 1-1 form. E to the power n-2 is an n-2, n-2 forms. F is a 2,2 form. So when you take the wedge product, you get an n, n form. And the easy exercise is to check that n, n form are the same as densities. So you can integrate. And you can also add the cosmological term here just by taking the cosmological lambda, constant lambda, which is fixed, and e to the n. For simplicity, I will not consider this here, but it can be done. Now, the relation with Einstein-Hilbert is very simple. You use the fiber metric to pair E with itself. This will give you a tensor field on M, and this is actually your metric. So the fact that this is non-degenerate says that this is also non-degenerate. Okay. And then you can take the other Lagrange equation here. So if you take the variation with respect to omega, you see that the covariant derivative of e to the power n minus 2 is 0. And if you use non-degeneracy, this turns out to be the same as just saying that the covariant derivative of e is equal to 0. And this is the same as saying that if you pull back this connection omega, what you get is, see? Probably I have to go back to. Okay. So, and what you see here is that, well, this condition is a torsion-free condition, which means that simply the pullback of omega is a Levi-Civita connection for this metric. Okay, so the first Lagrange equation tells you that the data are the same as in Einstein-Hilbert, and the second equation is equivalent to Einstein's equation. So the statement is that solution to the Palatini-Cartan, solution for the Palatini-Cartan model, modulo its own symmetries, is the same as solution to the Einstein-Hilbert formalism, modulo its own symmetries. So classically, the two theories are equivalent. Okay, now you can do this Bfv construction, then the simpler one, and this turns out to work only in 3 dimensions. In 4 dimension higher, it doesn't work, but you can do the AKSZ construction and check whether it's equivalent to the original theory. Okay, this is the case in n equals 3, and you have to see what happens in n larger than 3. So maybe, can I have just a couple of minutes?
Yeah, yeah, of course, no worries.
Okay. So here, let me describe the thing. So what do I ever do for this thing? First of all, I have to give you the classical space of fields on the boundary. So it turns out that this F sigma, the space of boundary fields here, turns out to be, well, to start with, okay, so first let me give you the statement and give you the construction. So what happens in dimension greater than 3 is the following. You can get a Bfv construction for the reduced phase space, apply AKSZ, and what you get is a different theory. It's a theory which has a different space of fields, so I mean, it's not the same theory, but you can compute a solution to its Euler Lagrange equation, so we call this theory PC prime, modulo symmetries, and this turns out to be the same as solution to the Euler Lagrange equation of Palatine-Cartan modulo symmetry, which is the same as what you want to have in Eisenheber. So you get a new Bfv theory, which is a Bfv theory for a theory which is classically the same as Eisenheber. So it's the same classical description of general relativity, but a different Bfv description. Okay, and this is a Bfv description that works because it's compatible with a boundary description. So our idea that this, if you want to work in the coframe formalism, this PC prime is the correct theory you should consider. And now, I don't know. I mean, this is the result. If you want to see the details, it's just a couple of slides. Okay. So, and this is based on these 2 papers. So the idea is the following. So, okay, let me do it in 4 dimensions. Actually, this is a physical case for simplicity. I mean, you can do it in any dimension, but let me do it in 4 dimensions, and let me set to 0 the cosmological constant just to simplify the formula. So here, the classical action is 1/2 E square F omega. So remember that here we had, right, e to the power n minus 2. So in 4 dimensions, it is just e square. Okay, so this is a classical action. Now what you do is take variation of the classical action, right? You integrate by part. The bulk term give you the Euler Lagrange equation, but then you get some boundary term, right? So when you take the variation of omega here, right, the variation of the curvature is a covariant derivative of the curvature. When you integrate by parts, right, use Stokes theorem, and on the boundary, you get 1/2 E square times delta omega. Okay? So this is the analog of the PDQ form you want to consider. So this is what you call the pre-1 form on the boundary, is alpha twiddle. Then you take its differential. This should be your symplectic form. In this case, is E delta omega. And the problem that these 2 forms turns out to be degenerate, right? Oh, you see here. I mean, if you plug in a vector field of this form, so if you substitute for delta omega, you substitute some 1-to form V, which is killed by wedge with E, then this is 0. So there is, for sure, some vector fields that kill these 2 forms. So this 2 form is degenerate. Actually, the exercise is that the whole kernel of these two forms is the span of vector fields with this property. Okay. So you can do the symplectic reduction, so it turns out that the correct space of boundary fields consists of 1 forms E that are on sigma that are non-degenerate, cross connections omega, modulo this equivalence relation that you can translate omega by some V that satisfy this condition. Okay, so now the space of boundary field is described as a quotient space. Okay, so this is not very good because, well, it's not good to work with a quotient space, and it's more difficult to determine this constraint space sigma in the quotient. So it's better to replace this quotient by some section of the space, and we can do it actually. So now I work locally on the space of fields. So pick some non-degenerate E0 and work in a neighborhood in the space of fields of this E0. Okay, so for this E0, since E0 is non-degenerate, so this means that actually, so now we have three components of the zero, is a one form on the boundary sigma. So the non-degeneracy says that their image in V is linearly independent, but it's not the basis because V is rank 4. So, but you can certainly add one basis vector. Okay, so we fix with some E0, and then for this E0, we pick some 0, 1 form such that this is a basis for the section of V. Okay. And now in the neighborhood of E0 in the space of fields, so it's a neighborhood U, the point that this En we still complete E to a basis. Okay, this is an open condition. So we fix some reference E0, we fix some En that completes the basis E0, but this En will complete any basis E in the neighborhood of E0. Okay, so these are the data. Okay. And now the idea is that we can take this F sigma intersection, this neighborhood, right? And instead of describing it as a quotient, we can describe it as a subspace. So what we do here is we take the E as omega in non-degenerate 1, 1 form in this neighborhood cross connection. And instead of modeling out by this equivalence relation, we impose an equation. So the equation is that En, this En you've chosen here, wedge d omega E, should be in the image of E wedge with something. Okay, so this is an equation, and the exercise is to show that this is a symplectic space, and this symplectic space is symplectomorphic to this other symplectic space. Okay, so you replaced this quotient by this subspace. Okay, and well, this is true under some assumptions. So the first assumption is that, of course, E is a twin non-degenerate. This is part of the physical data. But the second assumption is, as in the Eisenheber case, that the metric induced on the boundary by E should be non-degenerate. Okay. So, but this is an assumption that we also had in the Eisenheber. Okay. So here is here. So if E induces non-degenerate metric on sigma, we have this description of the quotient. And so now we will work on this space F prime. And now let's look at the Euler-Lagrange equation. So we have two Euler-Lagrange equations. So the first is the omega E square, the omega E square equal to 0, which is equivalent to the omega E equal to 0 in the bulk. This is a torsion-free condition. And then we have Einstein equation, which are just the variation with respect to E. So remember the action is here. So the variation with respect to E is very simple. It's just EF equal to 0. Okay. So this is the second equation, and this corresponds to Einstein equation. Now, what you have to do is to restrict this equation to the boundary. Now, this is easy because these are differential forms. You just restrict it to the boundary, and this becomes conditions for the initial conditions. So the restriction of this equation to the boundary determine C sigma. Okay. So now what you have, C sigma is defined by these two equations on the boundary, and also this equation, because this is the equation that defines F prime. And now, the interesting remark is, I mean, the theorem is that this C sigma is quasotropic. This is what we want to have. But the interesting remark that we can prove this theorem because the equation, the omega E equal to 0, which is just a restriction of the Euler-Lagrange equation, using this additional condition that you have an F prime, is equivalent to the condition E d omega E equal to 0, plus the additional condition. Okay? So notice that without the additional condition, these two equations are not the same. In the bulk they are, because E is non-degenerate. But the non-degeneracy of E on the boundary is not enough to prove that these two equations are equivalent. Of course, this equation implies this equation, but not vice versa. Okay, but with the presence of this additional condition, and this is why we work in this space F prime, ensure that these two equations are the same. And the advantage is that, well, once you write the condition this way, it's easy to determine its Hamiltonian vector field, and so to check that C sigma is quasotropic. So the Bfv condition is very, very simple. So you take these constraints, e d omega e equal to 0, that's what we had here, and ef equal to 0. So notice that this is a 3-2 form, and this is a 3-3 form. So you write these in terms of Lagrange multipliers. So you introduce some Lagrange multiplier C, which by that's to complement this here, so it should be a 0-2 form, and some Lagrange multiplier mu here, which has to be a 0-1 form. So the Bfv formalism tells you that the first step is to write linear combination of the constraints using Lagrange multiplier, and then promote the Lagrange multiplier to be ghost. So these C and mu become odd variables of degree 1. Okay, so this is the Bfv action, and there are some additional corrections that you have to introduce so that S Bfv satisfies the classical master equation. Okay, and of course you have to introduce the momenta of C and mu. I would call them B and mu, and these are just forms of complementary degrees and of Gauss number manifold. Okay, and you can actually compute the dots. It's not very difficult, and actually it turns out that even though this is not really determined by some the algebra, this Bfv construction stops as a nest level, so it's linear in the B and mu variables. Okay, so this is the result of Bfv, and well, there is some actually observation that makes AKSZ construction a bit better. Namely, since the E are linearly independent, you can write a 0-1 form as follows: as the contraction of the given E with a vector field plus the given En and some functions. So instead of taking a 0-1 form, now we take a vector field and a function. Okay, and both are shifted by 1. Okay, now you have to do the AKSZ construction. So you pass from sigma to sigma across the interval, and you have to replace the coordinates. Now our coordinates right on this target are E, omega, C, psi, and psi n. Okay, so these are, and I will ignore the momenta, right? And you have to replace them by functions and one forms, right? And here I want to just consider a classical theory, so I will only write the terms in the AKSZ construction that have degree 0. Okay, so here I just take the functions. So E omega now are not forms on sigma, but functions on an interval. On the other hand, W is a 0-2 form on sigma and a 1 form on the interval. Z is a vector field on sigma and a 1 form on the interval, and phi is a function on sigma and a 1 form. Okay, now these are the classical fields of the theory, and then what you have to do is just, well, first of all, take my 1 form, which now is E delta omega, and substitute the fields and integrate over I cross sigma, and replacing the drum differential on I for delta. So you get this expression. And then you can do the same for these terms in the Bfv action, and you compute this term. Now become 3 terms because I split this term in 2 terms because of this construction, and you get all these terms here. Now the sum of these terms will give you the classical action of the new theory, and these E, omega, W, Z, and phi are the new fields. Now what are these new fields? Well, actually what you can do, you can sum up omega and W. So notice that omega is a 1-2 form on sigma, whereas W is a 0-2 form on sigma, but a 1 form on the interval. So they are both 1-2 form on M, on I cross sigma. Okay, so these are a 1-2 form, and you think of this as a new connection. Okay, so this omega prime, so omega plus W give you some connection on M, and you could do the same for E, right? So you want to produce a coframe E prime, so this should be a 1-1 form. So you start with E, which is a 1-1 form on sigma, right? And you add this term. So here E is a 1-1 form on sigma, but you contract it with this vector field Z. So this becomes a 0-1 form on sigma, but this Z is also 1 form on the interval. So this is again a 1-1 form. Okay, and similarly here, I think here there is some phi missing. Sorry, yeah, I should have written phi. This would be phi EM. Okay, so you can reproduce the fields of the coframe formalism, the connection and the coframe. The only point is that these E prime omega prime are not free because we had this equation star, right, in the definition of F sigma, and this equation star has to be satisfied. So the new space of field is a subspace of the original space of fields for the Palatini-Cartan form. It's not the same space of field, it's a subspace. Okay? There is some structural equation that is to be satisfied. On the other hand, if you sum up A, B, C, and D, you get the Palatini-Cartan action. So here it should be prime. Okay? So now you can compute the Euler-Cartan equation for these actions. Of course, you don't get the Lagrange equation for Palatini-Cartan because the fields are constrained, so also the variation are constraints. You get less equation, but then you have to add this new equation, and it turns out that altogether they are the same. So the Euler Lagrange equation for this new theory on this restricted space of fields is the same as, so solution is the same as solution to the Euler Lagrange equation of Palatini-Cartan on a larger space of fields. The difference is that this condition star here is a condition that defines the space of fields, whereas in Palatini-Cartan is part of the Euler Lagrange equation. Okay, and I think this is it. So sorry for the delay.
Very
Thank
good.
you.
No worries. So if you want to unmute yourself, we can give Alberto a round of applause. Okay, so first of all, thanks for the talk, and I will open up if anybody wants to ask questions. Just feel free to unmute yourself and ask. Anyone? Okay.
Can I have a question?
Oh, hi.
Hi, Alberto. Very nice talk. Thanks. So you said, you know, this formalism with AKSZ to get this Bfv works in 3 dimensions but not in higher. Is there an obvious reason why it doesn't work in higher?
No. So okay, so if you, it depends on the theory, of course. So let's suppose that you start from some parameterization invariant theory, right? So for example, it works well for BF, Chern-Simons, and so on. It works. Now for general relativity, in the Einstein-Hilbert formalism, it works. Go back here. In let's see, where was it? So in Einstein-Hilbert, it works in any dimension apart from space-time dimension equal 2, because there, of course, you have to add something, just right. But it works. The only thing that it doesn't give you the original theory, because AKSZ always gives the first order theory.
Yes.
So, but the first order theory gives you is precisely the first order theory that corresponds to general relativity. So it works in any dimension, in 4 dimension, 5 dimension. Not only
it always gives you a theory, but not necessarily the first order theory of gravity. That's what you're saying.
No, they're saying that in Einstein-Hilbert it works. It gives you the first order theory of gravity.
Oh.
It gives you directly the Bfv formalism for the first order theory of gravity. So that works in any dimension. In the Palatini-Cartan formalism, the coframe formalism, this works on the nose only in 3 dimensions. And it works in 3 dimensions because, well, it's a BF theory. I mean, Palatini-Cartan in 3 dimensions is a BF theory, which is itself an AKSZ theory, so everything has to work. But in higher dimension, it doesn't. And the reason is that, well, the Palatini-Cartan formalism in dimension 4 and higher has all this complication, namely that, for example, you start with this boundary theory, you have to do some reductions, and you have to be careful that the constraints are not nice if you don't choose the correct way to describe the fields. The other thing that doesn't work is that if you start from Bfv formalism for the coframe formalism in dimension 4 and higher, then you try to devise its boundary Bfv formalism. You have to do some singular reduction. So these are problems for the Palatini-Cartan formalism. I mean, they're not intrinsic problem of general relativity. If you do Einstein-Hilbert, there is no problem. The point that we would like to do things with Palatini-Cartan, because then we would deal with the differential forms. Actually, I mean, our next goal is to describe corner structure. And if you try to do it in the Einstein-Hilbert case, this is really a nightmare. It becomes really too complicated. Whereas in the Palatini-Cartan formalism, there is some hope. Actually, we have already some results for the corner. So that's why we prefer to study this formalism.
All right.
Classically, they are all equivalent, of course.
Yeah.
I have a question. Sorry, maybe this is really dumb and naive, but what does Einstein-Hilbert mean when you have corners? Like, because there you have yeah, what do you do with derivatives at corners and things like this?
Yeah, that's a nightmare. That's a problem. You have to understand what you do with the. I mean, there are two problems with Eisenheber. First, that it's not expressed in terms of differential form, so it's not so nice to restrict. But you can say, okay, it's still a tensor field, a contravariant tensor field, covariant tensor field, so you can still restrict. The real problem is the constraints for Einstein-Hilbert contain second derivatives.
Yeah. And
that makes it a nightmare to understand what to do.
Okay, right.
Whereas in the Palatini-Cartan formalism, the constraints contain only first derivatives. Actually, it's the drum differential applied to differential forms. Mm-hmm. So then you just integrate by parts, and you get immediately you get something on the corners. Then you have to reinterpret what this is.
Right. Okay, sure.
But you just blindly apply Stokes theorem, you get something for the corners.
So maybe can I also ask a question? So as far as I understand, so there was some BV description of this Einstein action and so on, but you wanted a new BV description which fits in this Bfv formalism. So what you can do now with the Bfv formalism? So this is the first question, and the second question is, so you mentioned Chern-Simons. So is Chern-Simons like Bfv theory of Young-Mills or whatever? How does it fit? Or if you apply AKSZ, what are you getting anything new, or does it help somehow?
Okay, so the first question is that again in Einstein-Hilbert this Bfv construction works on the nodes, so there is nothing to be done. So the new thing is to make it work for the coframe formalism, and our answer or our recipe is that you have to modify the usual coframe description in the sense that you essentially have to restrict the space of fields. And if you restrict a bit the space of fields and then you do BV formalism there, then everything's fine. So maybe in Palatini-Cartan, so let me again stress, what is the relation between Palatini-Cartan and Einstein-Hilbert? In Palatini-Cartan, I mean the coframe and the connection are free, right? Then you use the coframe to determine the metric, but still the connection is free. And one of the Euler-Lagrange equations tells you that the connection is torsion-free. Okay, so it's one of the Euler-Lagrange equation that tells you that when you move to the metric formalism, the connection is Levi-Civita, so it's completely determined by the metric. Okay? So the torsion-free condition is one of the Euler-Lagrange equations. In our intermediate approach, we still have coframe and the connection, and part of the torsion-free condition is a condition on the space of fields. And the remaining part is an Euler-Lagrange equation. Okay? So this is the first thing. Now, the second question is, well, why you want to have this compatible Bfv formalism? This is what I explained in the first part. This is what gives you a chance to do a quantization of the boundary. Okay? So, of course, coframe formalism, Palatine gravity could be really quite complicated, but in principle, this is the setting that works. And we apply this setting to several other theories. So you start with a good compatible Bfv formalism, and then you have this procedure to quantize it perturbatively in such a way that you get the quantization of the boundary operator and blah, blah, blah. I mean, the boundary operator of the boundary and blah, blah, and this works. So this is the motivation. Now, the other question was what happens if you apply AKSZ to the Bfv, for example, of Young-Mills, right? Then, of course, you don't get Young-Mills because you will get a reparametrization invariant theory. Okay? So this will give you some theory, some reparametrization of invariant theory. It has somehow the topological content of Yang-Mills. This is somehow equivalent to, well, essentially it's Yang-Mills where you freeze the Hamiltonian to zero. In Yang-Mills, you have constraints equations, gauge transformations, but also an evolution Hamiltonian, right? And doing this AKSZ essentially corresponds to setting the Hamiltonian to zero. Somehow you freeze time. And for example, a simple example where I think it's easier to describe is a two-dimensional Yang-Mills. As you know, this can be rephrased as a Bf theory plus a B square term, or B star B term, or B square times volume term, right? So that term is a non-topological term that describes evolution. If you go to the boundary, compute the constraints, compute Bfv, and apply AKSZ, what you get is just the Bf theory. So you just drop this deformation that produces Yang-Mills. Okay, so this is a...
And the Chern-Simons story?
On Chern-Simons, no, because Chern-Simons is itself an AKSZ theory. So this is the result. If you, and AKSZ theory works very well with all these things. So you can take it in the bulk, go to the boundary, do the AKSZ for the interval, you go back to the same AKSZ theory you had in the bulk. So AKSZ theory are invariant under all these operations. In particular, Chern-Simons works. So if you do this procedure for Chern-Simons, you get back Chern-Simons.
I have a question.
Okay. Yeah, sorry.
Go ahead. Okay. Yeah, thank you very much for the talk. I was wondering, since it's very interesting about differential forms, there's also Poincaré gauge theory of gravity, formulated in this sense, where the connection and the coframe are always, the coframe is always unconstrained. Also, the connection is always free, and you get it's classically equivalent to GR. Have you considered that? Have you formulated?
No, but probably this will be another example to consider. We explicitly considered all these Palatini-Cartan formalism. We started considering the Plebanski formalism, but we're still in the middle. But yeah, I know there are other formulations. It might be worth, I mean, if you can send me some reference.
Yeah, sure.
Yeah.
And I also have another, very naive question. Do you, can you tell us something more about quantization and if it's maybe renormalizable?
Okay, so all the explicit example of quantization we have done in this setting so far are for topological or almost topological field theories. So the normalization is not an issue, and the reason for us was actually to check that this formalism works, at least in these examples. The idea is that in principle it should work, but of course now you have to also implement renormalization. And of course, well, when you renormalize, you have to keep track what happens also to this boundary operator. Okay, so you just have to do renormalization also in presence of the boundary. So I mean, I think it should be possible to do it, and probably technically is not much more difficult than the usual way, but yeah, we haven't had time to do it. There is one way which probably is a bit easier if you work on cylinders. I mean, now I presented the story only for cylinders, but in principle, of course, you can do it on any manifold with boundary. But if you do it with cylinders, there is some simplification. At least formally, you can say what the result is. If, for example, if the target is finite dimensional, so but you have constraints, you can say formally what the result should be. And it's expressed in terms of some star product exponential. And then you might say that, well, okay, in the infinite dimensional case, you should get the same answer. The only thing that you have to regularize and renormalize the star product in such a way that this star product exponential is well defined. And this is essentially what Fred and Hagen collaborators did. So probably that approach works better. So these are actually very well in the new language, the very old renormalization approach, but well, it fits very well this description. So this will be another. This is another actual direction we are taking now.
Okay, thank you.
So I wanted to ask if you can. So from string theory, one gets these higher corrections to the Einstein-Hilbert action. Can you apply some of these methods to get some description of that?
I mean, so our method, okay, start from an action functional. So I mean, if you have of course the action functional with extra corrections, of course you can try to apply the method to the new action functional. So that's, I mean, somehow this is a bit actually it's algorithmic, so you can try to apply, and sometimes I mean success is not guaranteed. Sometimes you crash into some singularity, but you may try to apply it. I don't know if how to do it. I mean, you should try to formulate it in case you get terms well that are not really local as this way, but so they require extension to some higher dimension, like things like vast domino terms. I mean, for that I don't. I mean, we haven't developed the formulas to deal with them, but in principle, there should be some way. Probably you just have to work locally and then try to understand how to globalize again.
Can I maybe again ask something? So if you have this Bfv formalism, you have this action. So now you want to quantize it. You want to solve the quantum master equation. So is the result what you are getting somehow independent on the way you solve the quantum master equation, or is it going to be, or is it already determined by the, in some sense, under some equivalence, by the classical action, or is it going to be heavily dependent on which solution you take?
Well, okay. So to quantize, you have to choose a regularization, and so the regularization is such that you can now write down the Feynman integrals. You can make sense in some way of the quantum master equations, and you can check that the result is invariant under deformations of gauge fixing. The problem is, like in every other situation where you do this, it's very hard to see how the result you get in some regularization correspond to the result you get in some other regularization. It's expected to be the same, but I think there are no theorems apart in very special situations. So here, in the sense, I mean, I cannot even say how strongly it depends on the way you solve the quantum master equation, because you find a way to make sense, I mean, some regularization. And for example, for this AKSZ theory, the regularization is essentially going to compactification, Axel and Singer compactification of configuration spaces, and blah, blah, blah. And then there things works very nicely. But in principle, you might choose a different regularization, and well, of course, I don't know what you get. But this is a problem in every such approach to perturbative quantum field theory. I mean, everybody expects that different regularization should give the same result, but this is not a theorem. Of course, actually, something even worse happens, that the Bfv formula, even once you choose a regularization, or even if you're in a finite-dimensional case, the Bfv formalism only tells you that the result is invariant under deformation of the gauge fixing. But in principle, you could take two different gauge fixings that are not the formula one to the other and get completely different results. And actually, we can get very explicit examples in this theory. So yeah, actually, the theory is defined also by the class. It's defined by regularization and by the class of gauge fixing you choose.
Okay, I think I'll stop the recording here, and then if anybody wants to ask questions after that, we can do that.